Hello everyone, welcome to our Strength of Material class. I am Somesha Sanapati, Assistant Professor of Civil Engineering at Vedang Institute of Technology. In this class, we will start with a new chapter, that is bending stress in beam. So previously we have discussed shear force and bending moment and also calculated lots of numerical on basis of shear force and bending moment and drawn a lots of shear force diagram and bending moment diagram. So we know that due to external loading on a beam, bending moment and shear force will develop in case of beam. Okay. So to counteract that external loading, we have an internal resisting force developed within the beam. So that internal resisting force will be termed as your bending stress. Okay. So that internal resistance generated within the body will be termed as your what? Bending stress. So what is pure bending or simple bending? Generally, bending is usually associated with shear. First, we have calculated the shear. Again, after using that shear, we will calculate bending moment. We can remember that. So, however, for simplifying, but then to neglect the shear, we have bending moment. We just only consider the moment. We know that when bending moment is maximum, there will be the shear force will be 0. So when moment we consider, that does mean we have the 0 shear. And so if a length of a beam is subjected to constant maximum bending moment and no shear force, then that length of the beam will be your pure bending or simple bending. So I think you will not understand that. You have to understand from this diagram. So here we have that AB beam, and you can see AB is your overhanging part. Sorry, AB is your beam, and the load applied here at different points. Let's name it as C and D. So we have 2 point loads at C and D with W kilonewton. Okay, the total length is here your L. So after calculation of shear force with W and L, we will have the shear force diagram. So you can see at which point there is no or 0 shear force, there will be bending moment, and that is your maximum bending moment. So the point, the total length of the beam where shear force is 0, the bending moment happens is maximum. Okay. So next point is your the maximum bending stress for that part of the beam remains also constant. So you can see in this diagram that bending moment, if this is 5 kilonewton per meter or anything, so the total this length will be same bending moment. Okay. So in this diagram we have known this thing that shear force, if shear force is 0, the bending moment will remain maximum whole of the span. Next, what are the assumptions made in the theory of simple bending? So what will be the assumptions? The assumptions says that the material of the beam is isotropic, homogeneous, and it follows Hooke's law. We have already discussed what is Hooke's law. Next is what is isotropic and homogeneous. Okay. Here you can see the beam. Okay. The homogeneous and isotropic, that does mean isotropic and homogeneous. What it says? The whole material of the beam will be same. Okay, there will be no difference in all directions. Isotropic and homogeneous means this material is same in all directions and at every point. Here you have if steel, then this is also your steel, this is also your steel in every direction and in each point. And it follows Hooke's law. It follows Hooke's law means Hooke's law is your what? Stress is directly proportional to strain. It is your Hooke's law. So if your stress is increasing, also your strain will increase. That does mean it follows Hooke's law. Next is your the stress induced is proportional to the strain. I already said that the stress induced is proportional to strain, and the stress at any point doesn't exceed elastic limit. In our stress strain diagram, we have already learned about what is elastic limit. So here it says that the stress induced is proportional to the strain. Like if stress is decreasing with value of 10, also strain will decrease. Okay. So, and also third, the stress at any point doesn't exceed the elastic limit. Next is what? Transverse section of the beam that were plane before bending remain plane even after bending. So, first what? The external load will apply. Here, the external load is your W. After application of this W, the plane where the beam exists, that plane will not change. The plane remains will same after bending also. Okay, the third point says the plane of the beam will not change at any condition, also after bending. The beam is initially straight and having uniform cross section. Yeah, here you can see the beam is straight. Okay, always we can see in case of practically beam will be straight line and uniform in cross section. Cross section is what? You can see the beam always rectangle in shape. Also we can have circular square shape. So if this part of the beam is rectangle, the whole part of the beam will be rectangle. Then we can say it follows the assumptions. The cross sections will be, if the beam is circular, then the whole beam will be circular. If the beam is square, the whole part of the beam will be square. That does follows the beam initially straight and having uniform cross sections. Next, the modulus of elasticity is same for the fiber of beam under tension and compression. What is the modulus of elasticity? In our first class of strength of material, I have discussed what is modulus of elasticity. Modulus of elasticity is termed as capital E. It will be same for beam under tension and compression. We have already discussed tension and compression things. So for compression, compression and tension, the beam will be what? There will be no change. The modulus of elasticity will not change in any cases. Okay. So if in case of theory of simple bending, it follows all these rules, then we can say it will be in simple bending or pure bending. If it follows all these assumptions, then we will only tell that it follows simple bending or pure bending. Here are the assumptions. Here we have the definition. Okay. In this class, we have discussed what is pure bending and simple bending. In our next classes, we have discussed all the other things about bending stress. Also, we'll solve some numericals. Thank you so much.